Hello, my name is Marius and I will be presenting the paper titled 3D ear shape as an estimator HRTF notch frequency. This was the outcome of a semester project I did at the Sound and Music Computing Master Program at Aalborg University in collaboration with fellow student Riccardo Miccini and under the supervision of Stefania Serafin and Simone Spagnol, as well as Runar Unnthorsson from University of Iceland. So let's get into it. The broader field of research this paper is aimed for is spatial sound perception and rendering, of which one of the foundational blocks is the head-related transfer function. Head-related transfer functions are filters that describe the acoustic effect of the human head with respect to an external sound. They are formally defined as the ratio of sound pressures at the ear and in the free field as given in this equation. We can see that they are dependent on the frequency and direction of the incoming sound. Furthermore, it includes the effects of the human head, torso, and quite importantly, the pinna, which is the external part of the ear. All these are different from person to person, which makes the HRTFs highly individual. The aim of this project is to tackle this issue of individualization and work towards an accurate and handy procedure for predicting individual HRTFs from non-acoustic measurements. The focus throughout the project was on predicting the lowest frequency pinna notch, or N1, in the median plane. The reason why we focused on this is because N1 was found to be a critical cue for elevation perception, as well as the fact that there have been observed limited spectral changes compared to the median plane for azimuth variations up to 30 degrees. So moving plus minus 30 degrees from the median plane doesn't change much the progression of this first pinna notch. A lot of previous work has been based on the CheapPeak database, which is an extensive database of HRTF measurements for which 2D photos of the pinna were available. Based on this work, Riccardo and others found good correlation between anthropometric measurements and the HRTF features. This in turn led to Spagnol and Avanzini, as well as Miccini and Spagnol, to work on building some regression-based models aiming to predict the first notch frequencies of the HRTFs based on these 2D anthropometric parameters. For this current work, however, another dataset has been used, a rather new one, actually one that hasn't yet been released, but one that is built on a dataset that has, in fact, already been released, called the Viking dataset. This unreleased version of the HRTF dataset had an extra focus on measurements in the median plane, as well as having been carried out in an anechoic chamber at the University of Iceland. As regarding setup, a standard Kemar mannequin was used, and a Genelec loudspeaker, which was fixed at a distance of 1 meter from the mannequin's head, with elevation being adjustable via an L-shaped rotating arm. Another key aspect of the dataset used in this project is the availability of interchangeable custom-made pinnae. Particularly, pinna molds have been created based on 20 human subjects of various shapes and sizes, which can be seen in this figure to the bottom left. Subjects have been named A to S, and in particular, also we have made a pinna mold of a standard Kemar pinna. An important thing to note is that we have available 3D scans of all these pinna models, which allows us to investigate certain HRTF features with respect to 3D properties of the ears. Moving on to the more technical part, the acoustical responses have been measured via the logarithmic sweep method. Particularly, an exponential sweep signal has been generated at the Genelec speaker, and which has been recorded at the entrance of the ear canal via a microphone. With this information, the head-related impulse responses could be computed via inverse filtering, essentially removing the sweep signal from the recorded measurements at the entrance of the ear canal. The frequency response of the HRIRs that were just extracted are in fact the HRTFs. When looking at them, however, we noticed quite a lot of reflections and shadowing, which we thought are due to the torso. Therefore, we carried out an HRTF measurement for a new subject, subject Z, where we had a flat pina basically. So so we only had a microphone and no ear. The frequency response for this subject then isolated the effects of the torso and the head. Furthermore, we then derived a filter. We designed a filter to remove these effects. So we basically fitted this filter to the magnitude response of this subject, when applying this filter to subject Z, you can see the figure to the bottom left is a pretty flat response. This filter was then applied to all the other subjects as well. For the extraction of the notch frequencies at the various elevations, two methods were used. The first method was based on an algorithm proposed by Riccardo and others, which involved a series of signal processing steps aiming to isolate these notches more clearly. These steps involved windowing the original signal, or taking the autocorrelation of this windowed signal and further windowing, eventually leading to a group delay function where the notches beneath a certain threshold could be extracted. The second method was a more straightforward method, where we extracted the notches beneath a certain threshold directly from a windowed HRTF spectrum, where this threshold was varied from subject to subject as the mean of the spectrum magnitude between 3 and 17 kilohertz. What we found was that the two methods generally aligned, and furthermore we merged the two notch sets together. So if one method couldn't identify a notch but the other did, we still eventually had that notch as identified. An example showing the extracted notches for subject A can be seen in the figures to the right, where the black crosses represent notch frequencies. They can be seen more clearly in the surface plot on the top. As mentioned previously, our focus was on the lowest notch frequency track, which typically starts between 4 and 7 kilohertz. What we did was that for each subject we manually selected this track based on visual inspection. What we observed was that not all subjects show a clear N1 track, and in the cases where that happened, those subjects were disregarded. This left a total of 17 subjects. At the end, we were left with a total of 1,599 data points with which to play with. The figure to the bottom right shows the N1 track for all the subjects. Moving on to our analysis of the 3D pina molds and our desire to extract certain anthropometric features that could be correlated to the notch frequencies, we had the following approach. We went from the 3D scans to 2D depth maps, which are essentially pictures of the pina viewed from various angles in the median plane where the sound source may be coming from. This was done via a ray tracing procedure where we assumed that the sound is propagating via plane waves. What we did was basically send rays from the sound source towards a fixed grid of 100 times 100 points. This grid was chosen to be as the largest grid needed to project the largest pina at any elevation angle. Keeping this grid fixed allowed us basically to include the effects of the various sizes of the different pinae. Only intersection values above the microphone position were considered, and also shadowed positions were disregarded. That means that if we had multiple intersections from the same ray, only the intersection closest to the sound source would be considered. The figure to the top right shows an example of calculating such depth map at an elevation of minus 30 degrees for a subject, while the figure to the bottom right shows depth maps at multiple elevation angles. We now have all the ingredients to train a linear regression model, aiming to predict the first notch frequencies of the various subjects. What we can do is use the depth maps as predictor, but unfortunately the relation between the depth features and notch frequencies was revealed to be nonlinear when checking the assumptions for linear regression. Therefore, principal component analysis was applied to the data. Using the first 256 principal components, it captures approximately 98% of the total variance in the data, and also satisfies the assumptions for linear regression. The training was carried out with a leave-one-out cross-validation on the subject level, meaning that when evaluating the regression for test subject A, the training is performed on the data from all the other 16 subjects, and so on when changing the subject. The main metric for evaluation was the mean absolute error. The reason why a linear regression model was chosen was in order to be able to compare our results with previous work. Particularly, Miccini and Spagnol published a paper at last year's Sound and Music Computing Conference, where they built a linear regression model based on 2D anthropometric data. They focused on an elevation interval between -45 and 45 degrees. This choice is evident when looking at our results as well, as very few subjects show notches above 45 degrees, and notch tracks for elevations below -50 degrees are quite flat. Therefore, we decided to train two models, one on the entire data set for elevations from -80 to 90 degrees, and one where we only used data from elevations in the -45 to 45 degree interval. The table to the right shows the results of the two models. The mean absolute error and the R-squared value of the fits are shown for each cross-validation case, as well as the mean and standard deviation of all cases. A weighted mean of all the cases is also introduced, where the mean absolute error of each subject is weighed with the number of predicted data points for that subject. This calculates the overall performance of the regression model by equally considering all individual data points, and is a more consistent metric. It's more consistent with the evaluation carried out by Miccini and Spagnol. For our M1 model, we find a weighted mean of 532 Hz, which is a slight improvement to the 607 Hz found by Miccini and Spagnol. Another metric for evaluation is to find the percentage of psychoacoustically valid predictions, which has been found in previous literature to correspond to differences of around 10% between frequency notches. This means that if two notches are within 10% of each other, they are perceived as the same notch. We find that out of all our predictions, 71.27% of them are psychoacoustically valid, while in previous work, 61.2% were found as psychoacoustically valid. In conclusion, a method for predicting the progression of the first notch frequency in the median plane of HRTFs with respect to elevation has been proposed. This method makes use of 3D anthropometric data, which is a somewhat novel approach compared to previous work, and it also shows a slight improvement compared to similar regression-based methods which used 2D features as predictors. The method could of course be validated and further improved by including additional data, as well as different machine learning techniques could be considered for the training part, perhaps something like random forest regression, which would not be constrained to the assumptions of linear regression models. Future work can also address higher frequency notches in order to eventually build a perceptually convincing individualized HRTF set. A list of references used in this presentation is shown here. Finally, I want to thank you for your attention and say that I am looking forward to try and answer some questions you may have regarding the project. Yes, take care.
In this talk, we will be discussing methods for performing with feedback in virtual acoustic environments. We will start with a few sound examples of artistic works that we have recently developed in this area. We will then move on to contextualizing our work, speaking a little about the history of feedback in experimental music performance traditions, and mentioning some of the techniques used for generating, controlling and suppressing feedback. We will then conclude this talk with a look at our novel methods for working with feedback in virtual acoustic environments. Throughout this presentation, please use headphones or good external speakers to hear the sound examples that we will play.
Is it still day? Day? If you like. There's no other word for it.
Will it not soon be evening?
Come on, Billy. Get up. You're beginning to incommode me.
Will it not soon be night?
Day. Night. Sometimes it seems to me the earth must have got stuck one sunless day in the heart of winter, in the grey of evening. Come on, Billy. You're beginning to embarrass me.
Is there grass anywhere?
I see none.
Is there no green anywhere?
There's a little moss.
These two short excerpts are from two works, both of which were developed to explore the possibilities of modifying a virtual acoustic system to incorporate feedback generated by that system. The non-clapping sounds in the first excerpt and the non-piano and non-vocal sounds in the second excerpt are this feedback. So why are we interested in this, and how are we doing this? Musicians, artists and technicians have explored the incorporation of audio feedback into recorded and live performances for at least 60 years. That being said, for the purposes of this study, rather than exploring feedback usage in popular or song-based music traditions, we will focus on the use of feedback phenomena as the primary, or at least a significant component, of the sonic materials in live experimental sound practices. As we mentioned in our paper, a full discussion of the use of feedback within live experimental sound practices is not the purpose and is beyond the scope of our work. For those who are interested, there are many sources to explore in this area, but perhaps the most comprehensive survey on this topic is presented in Cathy van Eyck's 2013 book, Between Air and Electricity, and on her associated website. For now, as in our paper, we suggest that most of the ways of working with feedback in experimental music practices are best encapsulated in the following works. So Pendulum Music by Steve Reich, 1968, Empty Vessels by Alvin Lucier, 1997, Cathy van Eyck's Wings from 2008, The Speaker Feedback Instruments, an ongoing project by Leslie Flanagan, starting in the early 2000s and still continuing, and Nicholas Collins's Pea Soup, originally from 1974 and has been revised in various ways from about 2001 until 2014. Perhaps what all of us are attracted to, that is to say, what we share with many of these experimental artists, is a desire to explore the notion or perhaps create an aesthetic situation which gives the impression of artists just playing with air. Thinking about works that fall into such traditions, the following ideas and questions arose in our minds. Given that audio feedback is the result of a positive loop gain between one or more microphone inputs and the output of one or more speakers, and given that the acoustic properties of the performance space or the system will determine the feedback frequencies that can result, that is to say, the most likely audible feedback frequencies being determined by the lengths of the direct and early reflection paths between the microphones and the speakers, then, within the fixed geometry of a performance space, how might one go about modifying the acoustic characteristics of this space so that different qualities of feedback, or a wider variety of feedback frequencies, can be achieved with minimal intervention and minimal additional processing? It was quite clear that by exploring feedback within the context of virtual acoustic environments, we could do just that. Before jumping into virtual acoustics, let's quickly review ways to generate, control, and ultimately suppress feedback. While some artists do like to explore squealing or howling feedback sounds in their work, to shape feedback, to give it in some way a slightly malleable feel, it is helpful to know how to suppress it and or dynamically turn it on and off. Often, to utilize feedback in performances, we use techniques such as EQ bandpass or notch filtering, dynamic processing with compressors or limiters, frequency shifting, simple or complex phase or polarity inversion, physical gestures or motions which change or attenuate the feedback, changing the geometry of loop gain paths in a performance space or within an instrument, and using piezoelectric microphones rather than air microphones. All of these techniques are used to varying degrees in the works of Reich and the others that we've mentioned so far. Given that virtual acoustic systems require many microphones and speakers to operate in close proximity, similar ways must be found of suppressing the many potential loop gain pairings. Therefore, the architecture of typical virtual acoustic systems could allow for feedback to be dynamically turned on and off during a performance. When using virtual acoustic systems, the audience and performers have the sense that they are hearing sounds in a space other than the actual or the expected acoustic of the physical space they occupy. With these systems, in both commercial and academic settings, the simulations or oralizations are likely to have the acoustic characteristics of a specific concert hall or room, or perhaps an acoustic characteristic of a religious temple, church, or large cathedral. Thus, we might think of microphones and speakers of a virtual acoustic system as being placed and forming potential virtual geometries of such spaces. Of course, if virtual acoustic environments are dynamic, that is, we can constantly change the virtual space, then with minimal interventions, the feedback produced in these situations is no longer dependent on a fixed geometry. However, virtual acoustic systems are generally very expensive, so who's going to let you play with these? Over the last few years, we developed a virtual acoustic system, one that was easy to install, uninstall and calibrate, one that can operate with a variety of commonly available microphones and speakers, and one which requires no specific proprietary hardware or software. The virtual acoustic oralizations are generated with low latency convolution reverbs, and when running, musicians can interact and move freely in the virtual acoustic spaces without the use of headphones or close microphones. While developing this system, we found two ways or interventions that temporarily destabilize it. When we stop the interventions, the system resets and restabilizes by itself. We noticed that as the system resets and stabilizes, the feedback decays into the virtual environment, similar to how such frequencies might be expected to decay in the actual space. The first method to destabilize our system involves temporarily blocking the microphone speaker's signal path by placing a hollow object such as a cup, a drum, a box, etc. over the microphone. The resulting feedback is colored by the resonance of these objects as well as that of the virtual space. A second method, requiring no physical intervention, is achieved by inserting a variable delay into the feedback cancelling signal path, that is, the path used for the elimination of loop gain feedback conditions between our virtual acoustic system's microphones and speakers. If we delay this canceller signal, the cancelling will be misaligned in time from the signal it is intended to cancel, causing a reduction in the amount of feedback suppression. And so we get feedback associated with the digital lengthening of the microphone loudspeaker paths filtered by the cancellation signal and the oralization simulation, the reverb of the virtual space. In both of the initial sound examples from the beginning of this talk, we used this cancellation signal delay method. In the first sound excerpt, a 2-microphone, 4-speaker virtual acoustic system was used. This was done inside the Karma listening room using 4 of the speakers from the upper ring, with a microphone suspended in the middle of the room. We inserted the delay on only a single microphone and speaker combination. In the second sound excerpt, a single mic and speaker system was used, which were placed inside a disc lavalier. It is worth noting that in this first sound example, the virtual environment is stable. In the second sound example, it is dynamic. That is, it is continually changed as the piece goes on. It is important to mention that in our paper, we present both methods of system destabilization and restabilization in a reductive form. As seen here, we cover and uncover the microphone of a single speaker and microphone virtual acoustic system. And here we demonstrate our delayed cancellation signal path method of feedback generation on a similar simple system. In this simple configuration, we trigger a signal, a 300 millisecond pink noise burst, through the virtual acoustic system speaker. Each time we trigger this noise burst, we simultaneously change the amount by which the feedback cancellation signal path is delayed. Thus, feedback tones are introduced whose frequencies are determined by how the virtual acoustic simulation is articulated by the noise burst and by the amount of time by which the cancellation signal is delayed. We then reset the delay to 0, restabilizing the feedback cancellation signal path. This causes the feedback to decay in a manner similar to how such frequencies would decay in the actual space as auralized by the virtual acoustic system. So thank you, and let us know if you have any questions.
Hello, my name is Karolina Prawda, and I am a doctoral candidate at the Acoustics Lab of Aalto University in Espoo, Finland. And today I am going to present to you the work that I did together with Sebastian Schlecht and Vesa, the evaluation of reverberation time models with variable acoustics. So to begin with, reverberation time is the time needed for the sound energy to decrease by 60 dB from its original level after termination of the excitation signal. So this definition was formulated by Wallace Sabine over 100 years ago. However, it is still used nowadays, and the reverberation time, or T60, is an important parameter in room acoustics. However, this definition is good when we measure the reverberation time. However, how do we estimate the T60 in a room that maybe is not even built yet? So Sabine came up with a formula for estimating the T60 of a room, in which he took into account the room's volume, the area of the surfaces in the room, the average absorptivity, and the absorption of the air. However, the problem of the Sabine's formula is that for it to be accurate, the room must fulfill a list of requirements. First of them being that the sound energy must be equally diffused throughout the space, which means that walls should not be parallel, and there should be no big differences between the basic dimensions of the room. Also, the average absorptivity should be low, and the absorption should be uniformly distributed in the room. To improve this formula, Eyring came with his own model that is based on the mean free path between sound reflections and is suitable for rooms with high absorption. However, both of those models still assume that all surfaces of the room have the same average absorption. So to address this, Millington and Sete came up with their own formula, which does not assume that all the surfaces have the same absorption. It works well for the rooms with the surfaces that have different absorption. And further improvement was done by Kutruf, who assumed statistical distribution of the sound in a room and also took into consideration the room's shape and absorption distribution. However, all of those models, even though they acknowledge that the surfaces have different absorptions, they still assume that those absorption coefficients are more or less the same. So the first model that included geometrical aspects of the sound field with unevenly distributed absorption was introduced by Daniel Fitzroy. He assumed that there is a relation within 3 possible decay rates along the 3 basic axes in a rectangular room. A similar idea was introduced by Arau, who described the T60 as a geometric weighted average of the reverberation times in 3 orthogonal directions. Even further improvement was made by Neubauer, who noticed that both Fitzroy's and Kutruf's models were based on the concept introduced by Eyring. So he made a similar correction to Fitzroy's equation as was earlier done by Kutruf to Eyring's formula. And this correction was split into 2 parts, one for the ceiling and floor, and the second for the remaining walls. So to check whether those formulas work in real life or how do they work, we conducted measurements in the variable acoustic lab ARNI that is located at the Aalto University. The lab is equipped with 55 variable acoustic panels that are located on the walls and on the ceiling. The variable acoustic panels look approximately like that. They have a metal frame and slots cut out in the front surface. The slots can be closed and therefore the panel is reflective, or they can be open, so the sound can enter the panel where it is absorbed by the absorptive material. So we did measurements in 2 scenarios. In the first scenario, first configuration was where all the panels were open, and then in every next configuration, the panels were closed one at a time until all the panels in the lab were closed, meaning that the first configuration, all panels open, then the second, 1 panel closed, the third, 2 panels closed, and so on and so forth. And the direction of closing the panels is indicated here by the arrows. And in the second scenario, we still started with all panels open, but then each configuration, in each configuration, only the panels on the ceiling were closed one at the time. If you want to listen to the examples of measured impulse responses, please visit the publication's website. So having the measured values and also the ones calculated by the models that were presented before, we wanted to compare the results. And what we did was we calculated the reverberation times for 6 frequency octave bands. And here you can see an example of the plot with results. So the vertical lines on the plot indicate the end of one wall and the beginning of the next wall, as you can see here. This is the first wall, the second wall, the third wall, the fourth wall, and the rest is the ceiling. And also on the x-axis, you can see that the number of closed panels increases, which means that the absorption decreases in that direction. So here you can see the results for all the 6 frequency octave bands from 250 Hz to 8 kHz. And as you can see, except for the 250 Hz band, in all other bands, the models underestimate the T60 values in the room. Also, what you can see is that in many bands like 500 Hz, 1 kHz, and 2 kHz, when the absorption decreases, there is a non-linear increase in the reverberation time. And most of the models cannot repeat this increase. So what we did next was we calculated the absolute mean difference between modeled and measured T60 values and converted them into percentage. So as you can see in this figure, the Fitzroy's formula provided the best results and gave the smallest error, which in the best case was around 17%. The worst predictions, or the biggest error, was given by Millington-Sette's formula most of the time, and when the absorption decreased, Arrow's formula gave a bit worse results. So the same comparison we did for the scenario in which panels only on the ceiling were closing, and as you can see, the plots look a bit similar, and also on the x-axis, as the number of closed panels increase, the absorption decreases. So you can see here the full results for the 6 octave frequency bands, and the results are pretty similar with the first scenario, meaning that for the 250 Hz band, the modeled and measured values of T60 are somewhat similar, but in every other band, the modeled T60 values are much lower than the measured ones. And we again calculated the absolute mean difference between modeled and measured reverberation time values. And again, the Fitzroy's formula provided the best predictions, except for when the absorption decreased considerably, where the Sabine's formula is a bit better. And the smallest error in the best case was around 16%. And again, the biggest error was given by Millington-Sette's formula. So knowing that the models for predicting reverberation time that were presented in the study depend heavily on the absorption coefficient values, we wanted to check whether our results and our conclusions are valid or are correct. So what we did was we added noise to the absorption coefficients of floor, walls, and curtains. And we ran 1000 simulation where in each simulations the values of the added noise were different, and they were ranging from minus to plus 50% of the initial values of the absorption coefficients. And after this 1000 simulations, we could say that the story that we wanted to tell didn't change, meaning that most of the models still underestimate the reverberation time, and also that the Fitzroy's formula still gives us the smallest difference between the modeled and measured values. Here is a example of the plot with results that we made after this 1000 simulations. And if you want to see more, please visit the publication's website. So to conclude this presentation, as we could see, the models to predict the reverberation time are quite inaccurate. And in our case, the best predictions were achieved with Fitzroy's formula. However, the biggest errors were given with the Millington-Sette's model. What was surprising is that this 100-year-old Sabine formula performed actually pretty well. However, one of the most important conclusions here is that a more accurate and flexible method for estimating the T60 is definitely needed. So here you can see some references that I used in my work. And I thank you for your attention, and I hope to receive some questions from you. Thank you.
Hello to everyone. I'm Louena Shtrepi. I'm a researcher at Politecnico of Turin, and I welcome you to this session. Which I'm really glad you could follow. And I would also like to thank the three presenters for their interesting works. And I would go on with a few questions. So I would warmly invite you to write on the chat on the YouTube channel your questions. I've seen that someone has already started. For our first presenter, I would start with a question. Regarding the HRTF accuracy in measurements, how much accuracy is required in order to perceive the difference? You have done a lot of work into the details of the measurement points and so on. How necessary is all this, and to which aim, I would say?
Yes, so basically, I think I also mentioned it in one of the slides. We investigate based on something called psychoacoustically valid data point predictions, and that's was found in previous work to be around plus minus 10%. So depending on the frequency, you have to be within a range of plus minus 10% of your target frequency. But of course, this is just some previous work, and we don't know the setting of those experiments exactly. So I think ideally one would move on and use these results and do some sort of a perceptual evaluation and try to compare with this previous work, and also basically evaluate our own models. Mm-hmm. Yeah.
Yes.
But yeah, in the paper is roughly plus minus 10%.
Plus minus 10%. And yes, my further question on this was how much the number of listeners or the number of testers that you investigate influences this accuracy. So is there a size effect on this?
On this limit of plus minus 10% for the psychoacoustically valid?
Yes.
I'm not sure right now about that particular paper from where we took this reference, how many persons they had in their tests. But I would imagine that it shouldn't be dependent on the number of people that you test. Of course, like if you would just test a very small amount of people, you would have some statistical randomness. So it might be that sometimes it would be more or less, but if you test enough people, you should somehow converge to this value that they talk about.
Mm-hmm.
Yeah.
Any other questions from the audience? Because I have a lot of questions on this topic. It's very interesting.
Yeah, I mean, I'm looking.
There's a question to Karolina, if I might chime in.
Yes.
It's on the YouTube chat.
Karolina, are you planning on making your own reverberation time formula based on our measurements?
Well, maybe I am not planning to do it myself because, to be honest, it's quite a complicated task to like come up with some model, especially that, as you can see from my presentation, most of these formulas still most of those formulas still miss something. They still can't be really accurate. So I think that there is something really more, much more needed than just let's say simple formula. But I've heard and I know that some researchers are working to provide better estimates of reverberation time in the room. So there is that research coming, and when it comes, I'm sure to have it also tested in our variable acoustics laboratory.
That's very interesting. And I would also add, if have you also planned to test a combination of absorption and scattering surfaces? As you might have read, there are a lot of there is a lot of research nowadays that is studying the combination of these two kind of materials, since they influence a lot the sound field. And therefore also the sensitivity of these formulas is related to these conditions and how these two kind of materials are combined.
Yes, so there are plans to see how different type of surfaces, like more diffusive, more the ones that more scatter sound more, how they affect this reverberation time for formulas. Or the accuracy of predictions. However, well, this is just something that we plan now. For now, we can't, like for this paper, this presentation, we couldn't provide such research because, like for now, we don't have that type of space that would have, let's say, the controlled number of diffusion that we could change. Like here we change the absorption, the amount of absorption. So we don't yet have like similar space where we also can have the control over the scattering of the sound. So we hope that we'll have that space in the future so we can explore this topic some more.
And yes, we have also another question on this. Do you think that measuring different rooms would lead to different conclusions? And I think here with different rooms, maybe it's meant that different volumes, and we would expect that with different volumes or shapes, you might lead to other results. Have you tested this in a preliminary way?
We haven't tested that yet, but I agree that, of course, like different volumes, different shapes will affect the accuracy of this reverberation time formulas quite a lot. However, also kind of my argument is that those formulas are very widely used also in kind of commercial use. So to predict reverberation time in smaller rooms, in classrooms. So it's I think worth to say that we should be very careful when maybe predicting the reverberation time with the rooms that are that reverberation time formulas were intended for. That we should not maybe based on those results like trust them 100%. So, but I agree that probably for rooms with like bigger volumes, they could be more accurate. Yes.
Mm-hmm. Okay, thank you. Is there any other question? I would ask our second presenter whether you have tested the influence of the background noise on your system. How it would influence the adaptivity of this method?
Good question. Well, if something is audible when you turn the cancellation off, anything that's audible is going to contribute to what comes out. And so, for example, in the piece in the disc clavier, the fan noise is quite close to relatively close to the microphone. So a little of that seems to bleed in to the feedback that is produced. In terms of the overall feeling of reverberation in the system without us messing around trying to generate feedback, it doesn't seem to have a large effect. The background noise, like once you calibrate in the room and things are relatively stable, it stays the same. Temperature, put it this way, drastic temperature change makes a larger effect to the feedback cancelling than anything else that we've experienced. We haven't tested that as such, but we have noticed when we crammed a bunch of people into the studio and the temperature went up, you could really get a difference. Whereas everything else seems to be, so far has seemed to be fine. We haven't totally tested all of that.
And which do you think there are the limits of this method?
Say that in another way. So the limit would be in the shape of a room in terms of if the listener is very close to a boundary wall and they're obviously getting the actual reflections of the space that they're in, that can be quite distracting. Is that what you mean? That's one limit of what we're doing. The other limit, say, would be within the piano piece as well. You've only got a single speaker generating, so it's not so much generating an acoustic as in a kind of an effect. It gives a sense of prolonging the decay of the piano. It gives a little bit of sense of kind of, oh, there's another space, but it's not the same as having four speakers around you and being immersed to a certain degree.
I see.
Mm-hmm. Okay?
Okay.
Yeah.
Is there any other question? Thank you. From the virtual audience? No? Mm-hmm. Maybe there was the question from our Skype chat. If you want to answer to that.
Oh, somebody asked me about the feedback on Beckett. I would say, yeah, there's a little bit. So somebody asked me if there is a connection between feedback and Beckett in the work. I suppose in terms of the theatre circular kind of idea, and in a lot of those pieces as well, there's this the dialogue. You know, what's the famous thing about Beckett? Like, you know, he manages to do nothing twice, but within that nothing, when each kind of section of that, there's these little waves, these little peaks of kind of energy, and then it dissipates and goes away. So that kind of that rhythm is kind of built into the plays, and it just makes it really, really useful when you're trying to generate feedback. And there's certain moments where the voice raises up, catches on when we turn the feedback system, when we turn the cancellation off, and just, yeah, we tried a lot of other material for that kind of speech generating feedback. That rhythm that's inbuilt in the Beckett stuff just works really, really well. And yeah, so that's why we did that.
Okay. Well, thank you to all for attending. I will give the word to Andrea.
Okay, here I am. And thank you all. Thanks to our speakers, to our chair Louena. I'm just here to tell you that it's been a long day, but I think it was been very rewarding. Now, in terms of scientific program, we will be back tomorrow, and tomorrow in particular at 12 Central European Summer Time. And I have to remind you that, of course, this evening is not finished yet, because at 9:45 there is the first music session. We have 6 pieces that will be streamed on our channel, and in particular this music session is devoted to binaural pieces. So wear your headphone and listen to those pieces. You have 1 hour right now, and you can then be back here on our channel. So thanks to all, thanks for your work, and see you later and tomorrow. Bye.